Hey everyone, and welcome. Today, we're going to dive into something that sounds like pure science fiction, but it's very real. How do you actually land a spacecraft on a tiny, tumbling rock millions of miles from home? Let's get right into it.
And really, this is the heart of the problem. You gotta ask yourself, how do you park on a giant, wobbly waterbed in the dark? Because landing on an asteroid, well, it's nothing like landing a plane. It's this incredibly delicate, high-stakes dance in an environment that's actively trying to fling you back out into the void.
And that brings us to the first big mental shift we have to make. Forget everything you think you know about landing. On an asteroid, you're not parking at all. It's more like docking with the International Space Station, but your target is a spinning, unpredictable potato. Okay, so take a look at this. On the left, you've got Earth. Gravity is our best friend, right? It keeps our feet on the ground, nice and simple. But on the right, that's the asteroid. That's our wobbly waterbed. We're talking about gravity that's often less than 0.1% of Earth's. So what does that mean? It means any force you use to touch down, even a tiny nudge, isn't absorbed. It just pushes you right back. It's like trying to land on a trampoline. One little bounce, and you could be sent flying off into space. You don't get a do-over. So getting a handle on microgravity is a huge deal, but honestly, it's just the start. The surface of an asteroid is an incredibly hostile place. You've got all these other dangers you have to deal with, all at the same time. First off, there's the spin. A lot of these asteroids aren't just flying straight, they're tumbling end over end through space. Imagine trying to jump onto a moving merry-go-round, but you're blindfolded. That's what this is like. You have to match its speed and its rotation perfectly, or it's game over. And this isn't just a what-if scenario, this is real life. When NASA's OSIRIS-REx spacecraft got to the asteroid Bennu, it found the thing was spinning completely around once every 4.3 hours. So think about that. The entire 4-hour-long descent had to be choreographed to match that spin perfectly. It's an absolutely mind-boggling orbital ballet. Okay, next problem, the dust. Here on Earth, dust settles out of the air, no big deal. But in microgravity, it just floats. A single touch from your spacecraft can kick up this cloud of fine, sticky particles that just hangs there for hours. It's a lingering fog that can blind your cameras, scratch up your lenses, and just clog up all your delicate machinery. A total nightmare. And to top it all off, you often don't even know what you're trying to land on. Is it one big solid rock, or is it what they call a rubble pile? Basically, a loose collection of boulders and gravel that's just barely held together by its own weak gravity. Landing on one of those is like stepping onto a giant pile of gravel. The ground could literally shift or collapse right underneath you. It's a game of surface roulette, which is why you have to map the heck out of it before you even try to get close. So yeah, the challenges are just immense. But this is where the genius of engineering comes in. Scientists and engineers have developed this incredible toolkit of solutions to actually anchor a spacecraft to these crazy, unpredictable surfaces.
Let's start with one of the most direct ideas. A harpoon. I mean, it sounds simple enough, right? You literally fire a hook into the surface and reel yourself in. But this is a perfect example of why you have to know your target. Back in 2014, the European Space Agency's Philae lander tried exactly this on a comet. The problem was, the surface was way harder than anyone expected, like concrete. The harpoons didn't anchor, and the lander just bounced. It ended up tumbling across the surface. It was a really tough day, but boy, did we learn a valuable lesson from it. But harpoons are just one tool in a much bigger toolkit. You've got the harpoon, which is kind of like a fishing hook for solid rock. For those loose rubble piles, you could use an expanding foam that basically glues the pebbles together to make a solid anchor. If the asteroid has a lot of iron, hey, why not use super powerful magnets? And for really chunky, bouldery surfaces, you could use grapples, basically just like climbing hooks. The key thing here is there's no one-size-fits-all solution. You've got to pick the right tool for the job.
But then you start to think, why even risk a full landing? What if you could get what you need without sticking around? Well, that's the idea behind an incredibly elegant solution that avoids a ton of these dangers by minimizing contact. It's called the touch and go, or TAG for short. And NASA's OSIRIS-REx mission absolutely perfected this technique at Bennu. You can see the whole maneuver here. It was this slow, careful 4-hour descent for just 10 seconds of contact time. That's it. In that tiny window, the spacecraft shot out a blast of nitrogen gas, which kicked up a bunch of dust and pebbles and basically vacuumed up a sample. It was like this quick, perfectly timed kiss to the surface, in out and away to safety with more than 60 grams of amazing asteroid material.
Now, Japan's Hayabusa 2 mission took a similar idea, but made it even more dramatic. It didn't just find a good spot to touch, it made its own. The spacecraft actually fired a copper projectile into the asteroid Ryugu to blast a brand new crater. Then it swooped down to grab samples from inside that crater, material that hadn't seen the harsh radiation of space for billions of years. Just an absolutely brilliant and bold move.
So where do we go from here? Well, the tech for exploring and maybe one day mining these asteroids is getting even crazier, and a lot of it is actually taking inspiration from right here on Earth, from nature.
I mean, look at this thing. This is a prototype for a six-legged robot that's basically a space spider. It uses 3 of its legs to walk, and the other 3 have these specialized claws for gripping onto loose, uneven ground in almost zero gravity. It's perfectly adapted for that environment. And there are other wild ideas too, like sending up swarms of simpler, soft-bodied robots that could work together to gently take apart a rubble pile piece by piece. Okay, so let's do a quick mission debrief. What are the big things to remember? First, the physics is totally different out there. Force is your enemy. Gentle precision is everything. Second, the environment itself is hostile. You've got to plan for that merry-go-round spin and all that sticky dust. Third, you need the right tool for the job. Your toolkit is critical. And finally, automation is absolutely key. The communication lag is just too long. These robots have to be smart enough to think on their feet.
And really, this quote just says it all perfectly. We've learned how to turn these wobbly waterbeds into stable work sites. Through incredible cleverness and learning from mistakes, we're actually figuring out how to work in this totally alien environment. These chaotic floating rocks are slowly but surely becoming our next frontier.
Which, of course, leaves us with one final, very exciting question. Okay, we've figured out how to get to the asteroid and stick to it. We are on the rock. So now what? How do we actually start digging in and harvesting this high frontier? Well, that sounds like a story for another time.